Hello, and welcome to our presentation for RGBT-Dog, a parametric model and pose prior for canine body analysis data creation. While there exists a great deal of labeled data for human body analysis, the same is not true for animals. Mainly creating new labels for the full range of animal species would take years of effort from the community. To address this, we present a new, large-scale canine motion capture dataset and parametric canine body and texture model, RGBT-Dog. These are used to produce the first large-scale, multi-domain, multitask dataset for canine body analysis, comprising of detailed synthetic labels for both real images and fully synthetic images in a range of realistic poses. We also introduced the first variational canine pose prior, which is used to fit the parametric model to images of canines. Like other parametric models, RGBT-Dog is defined by a set of parameters, in this case shape, texture, pose, and root translation and root rotation. Beta and gamma are used to generate a mesh shape and a texture map from PCA spaces. Theta is used to pose the skeleton of the mesh, while root rotation and translation are used to place the mesh in 3D space. These can then be used to generate data labels. For our PCA shape space, we build upon the shape space of RGBT-Dog from Kearney et al., where we use the same photogrammetry scans for 11 real dogs. These have been further refined by a digital artist for greater detail. A number of the associated meshes for these scans are shown here. Our PCA texture space is built from the texture maps resulting from 12 photogrammetry scans. Here we can see the dog textures as UV maps produced from the cleaned photogrammetry scans. This texture space can then be explored using our texture parameter. Here we can see some visualization of our texture space for the first 4 principal components of the PCA space. We also show the effect of posing the mesh with motion capture data. Our pose parameter theta is used to pose the skeleton of the mesh resulting from the RGBT-Dog model. To generate pose, we make use of our new motion capture dataset. We build upon the motion capture data of RGBT-Dog by Kearney et al. We have expanded upon this dataset with additional dogs to provide the largest set of canine motion capture data for the community. Data was captured under the same conditions as RGBT-Dog, with additional dogs included. A breakdown of the motions performed is given in the table shown here. With this large set of motion capture data, we were able to create the first variational canine pose prior. As far as we are aware, this is also the first pose prior for animals in general. We create this prior using the same methodology as the V-poser prior in SimpleX, due to its success for human poses. This pose prior can be used to generate realistic poses, but is more useful to us as an inverse kinematic solver for fitting RGBT-Dog to real images. We can generate data using RGBT-Dog in 2 ways. Either A, fully synthetic images and data, referred to as synth data, or B, create synthetic labels for real images from existing datasets, which we refer to as pseudo-ground truth or PGT data. For synth data, we randomly generate parameters, except for pose, which is pulled from our motion capture dataset. For PGT data, we fit RGBT-Dog to the real images of Who Left the Dogs Out by Biggs et al. This is accomplished using our pose prior and other optimization terms similar to SimpleX. This generates a set of RGBT-Dog parameters. The RGBT-Dog parameters, be they for synth or PGT, are then used to create a mesh, which is then rendered to create the data labels, and in the case of synth, an image. Full details regarding this data creation pipeline can be found in the main paper. This rendering creates a set of multitask data labels. Silhouette and part segmentation maps are created by applying the appropriate texture maps to the canine mesh and rendering the resulting mesh. The part segmentation texture map and resulting part segmentation mesh are shown here. 3D and 2D key points for the RGBT-Dog skeleton are obtained from vertex regression and projection, as is standard in parametric models such as SimpleX. We can see the regression from the vertices here. Some examples of data points for both synth and PGT can be seen here. Do note the white label in the maps for the PGT data. This is an unknown label used to prevent accidental mislabeling during the fitting process. Here we provide some visualization of the results from fitting RGBT-Dog to real images. One can see our mesh reconstruction efforts resulting from the fitting of RGBT-Dog and our model's increased skeletal key points compared to the ground truth provided by Biggs et al. We can use this data to train models for common computer vision tasks, pose estimation, and part segmentation. We use stacked hourglass models for both tasks and present some results here. These results are not intended to be state-of-the-art, but rather to demonstrate the utility of our model and data. Here we can see some results for 2D pose estimation. As can be seen here, our model can generally perform well on points such as the spine, neck, and face, but begin to struggle more towards the lower end of the extremities of the legs, and particularly the tail and ears, where we see noticeable flaws. These next two slides show results for part segmentation. We see that our trained part segmentation model can correct inaccuracies in the ground truth produced from fitting the model. This is most obvious in the third column from the left and the last column from the left, where the model has corrected the mistaken labels and filled in the unknown label with the correct labels. We applied our trained part segmentation model to images of non-dog animals. Surprisingly, the model performed very well for many of these species, despite the extreme differences in body shape. Additional results and pose estimation results for other animals can be found in the main paper and supplementary material. To summarize our contributions, they are as follows. Number 1, a new canine parametric body model, RGBT-Dog. 2, the first variational canine pose prior. 3, a large-scale canine motion capture dataset. And finally, 4, a large-scale multitask multi-domain dataset for canine body analysis. Thank you for listening to our presentation. Further details can be found in the main paper and the supplementary material.